Okay, so here we go. We're going to do some single slit diffraction. Going to clean up the lecture that I boogered up on Friday. So just going to get to the main ideas of the math, and then I'll clean up some of the rest, and we can talk about the properties of thin film interference, not thin film interference, the single slit diffraction. But let's just try to get the graphs and the pictures done, and then we can worry about the rest of it later. So what we're going to start with is the idea that we're working with a slit, so that the slit width, this is going to be that's kind of fat for me. Let's try that again. Okay. Nope, too small. Yeah, that's better. All right, so we're going to do single slit diffraction. And although I won't be able to draw straight lines, you guys will be okay with me because it's really about the triangles we're going to draw. So let's start with this. So we have a single slit, and our slit width is going to be, I'm going to use a W to represent that. And so when we're working with this, the first thing we want to note is that because of the weird properties of light, when the width of the slit is really close to the wavelength of light, or if we're talking with sound, if the width of the crack or the door opening or whatever is close to the wavelength of sound, ocean waves, of course, with piers and docks and boats, anytime you have the width of the opening being about the same size as the wavelength of the wave that is trying to pass through, you get diffraction. You get it even if the slit is much, much bigger, if there's a big gaping hole or gap instead of just a small one. But the diffraction you see in those situations is not as apparent. So I'm going to pull up a video, an image for you so that we can talk about this a little bit, and then we're going to come back to the single slit diffraction piece. And so what I want you to realize is that we're going to treat all of this, as if we have perfectly constructive and perfectly destructive all the time. In fact, we do not have perfectly constructive and perfectly destructive light all the time. We have places in between, and if you're looking at this intensity graph, if you look at the intensity, as you get towards the edges, there's the central bright maximum, and you can see it's noticeably larger and brighter than the other two on either side. The first bright fringe, the first maximum after the central maximum, you'll notice the central maximum starts to get a little fuzzy, and the one on the top and the one below it are fuzzier, and then it gets even less apparent how clean. You don't get a nice clean edge. It's a blurry picture a little bit, but you can clearly see that you have these sort of repeated patterns above and below. So diffraction occurs like that, and one of the things I want you to see, single slit diffraction images, hang on just a second. There's another one I want to show you, and it's this one. This is a little bit better. What we really get is that if we have a small slit, and you can see that the slit in this case is small compared to the wavelength of the light that's coming, it sort of acts like you took the laser from behind the screen and you put a laser in front, or you dropped a pebble in a pond. And as you drop this pebble in the pond, what you're going to see is that the waves radiate outward. Just like if you drop a pebble in a pond, you get circular wave fronts coming out from that. Those circular wave fronts are going to indicate the crests, if you will, or the crests, and in the white parts in between would be our troughs. And so what we're looking for here when we see this, if you can imagine taking a bunch of light rays and you run them through this, which I'm going to show you right here, those light rays, the waves are going to come, you're going to hit them at different places on the wave. And so you get perfectly constructive interference when you have all the waves line up exactly, when you really do get that every crest, every trough, every point by point lines up. And then you get some blurry. So we go from bright red to lighter red, then dark, then lighter red, then black. So these in-between states are your, depending on if you're a positive person or a negative person on your outlook, You could call those partially constructive regions or partially destructive regions. You'll notice that as we go out, the light becomes dimmer and dimmer, and you can see that the wave gets dimmer and dimmer because we're moving from perfectly attuned to out of phase, to somewhat out of phase. And so when we're doing this, what we've got going on, let me come back to my screen, is that we have a whole bunch of lines, okay? I'm going to see if I can get this to work for me. We have a bunch of lines that would be nice and parallel coming through, and we have these wave fronts radiating out. And so what we're looking at with this is, let's imagine for ourselves right here that point P is a bright fringe. If point P is a bright fringe, what I'm really saying is that, let's erase these cute little wave fronts, is that when waves get to this location, from wherever they come from and whatever the angle they come in at that moment in time, we have constructive interference. Now, we're not going to worry about it's bright here and then it kind of dims out on the sides and then you get a really black spot. We're just going to go with the big ideas of kind of locating the center of each of our bright and dark fringes. So to do that, let me get the screen back up here. If we were to draw these, let me draw these little tiny wave fronts. So here's our little tiny wave fronts. What we're trying to see is, let's imagine that we had, here's one ray coming from there, and here's another ray coming from there. So what we did, the argument we're making is we have a distance 1 and a distance 2 of where we're connecting crest to crest to crest all the way across. But then we're going to draw a new triangle over here where this is the slit width and we have a right angle and here's our triangle. So that's going to be our first triangle that we're going to consider. And when we do that, I'm going to bring him out over here so we can look at that triangle a little bit better. Actually, made that one a little bit too long. So what we have here is we have an angle, we have the width of the slit, and we have an extra path because our wave is going to continue. What we're really looking at is, let me erase this for just a second. I'm going to take these off. What I'm really looking at is the wave is doing something like this. And this wave is also doing something like this. And this extra distance, this x, is the extra distance that the second light wave had to travel, the extra distance it had to travel that's longer than the first wave to arrive at point P because they're at different distances from point P. So x is the extra distance. So if we call this angle theta, x over w would be the sine of this angle. So x, my extra path difference, is w times the sine of theta. So that's the first triangle we want to consider. Now, once we've done that, we want to use a little more geometry here, and we want to imagine for a second if we had all these parallel lines, all these parallel rays. If I was to take a line and connect it down here and come across, that's the triangle we were just looking at. So let's now take our picture that we had a minute ago and let's come here and let's zoom in on what happens here. So now instead of being a small slit, we're going to see a really big slit. Well, the reality is that light interferes with itself, and we really have a hard time thinking about that because if you take a light packet, which we call a photon, and we shoot it at the screen, so here's our photon, and we shoot one at the screen, we're shooting it here, it makes no sense whatsoever that what I would see is a central bright, and then we get the little lumps on either side, and they diminish in size and they peter out. Well, thank you for thinking that's what I was drawing. But anyway, so this light wave, this particle, this photon, though, starts to act like lots and lots of photons. One that bounces off, one that goes there, one that goes here, one that goes straight in, some that get blocked over there, and that's part of the reason we get this interference pattern. So what we've got when we look at what's happening here is our photon that was sort of shot in the middle of the slit sees the slit as two half-size slits. So for example, if we had a 2 centimeter wide slit, it acts like two 1 centimeter slits. It's sort of how the behavior goes, so that the photon can have one guy over here and one guy over here, and it's interfering with itself. And I know that's bizarre, okay? I get that is just dangerously bizarre. But if we can imagine, let's say, I think I'll be easier going down than up. So let's imagine if there's if the photon here comes in like so, then there's a matching photon in the other half that does the same thing. If there's one in the middle, there'll be another one in the other half that's in the middle. And what we're looking at as we zoom in is all these little photons, all these little ray paths that we see, they all have a cute little friend on the other side that lines up. So that if we do what I just did, which is take a line, I make one side of my triangle here. Whoops, not so good, Joy. One side of my triangle here, and then I try to stay perpendicular to all those. I didn't do a great job of that. I think I do a little better. May not be able to do great better. Then we end up with each one of these triangles having a different extra distance. So this would be, this one was doing this one was doing this, and so forth and so on. So all these little guys have different wave distances. This total distance is my W. This is a right angle, and these are sort of partner photons. So what I'm looking at is the distance from here to here is this x that we're looking at, that is W sine theta. So this is the extra path difference. Now, when we do this, let's go to one more picture. So you can see that before I leave this, all of these have the same side over here. They all have the same hypotenuse, and they all have the same angle. So as we go out, these triangles, these new triangles, will be similar, meaning that they have proportional side lengths. And we're going to use that idea that the side lengths are proportional to give us the idea that each x1 might be 1 times W sine theta, and x2 might be 2 times W sine theta, and x3 might be 3 times, so forth and so on. And that's going to give me each wavelength, or each path, each extra path difference is going to be a multiple of the very first one we do, because the ratio of the sides is similar and the angles are all the same, which makes those similar triangles. Okay, so now let's go back to the zoomed out version and let's do one more thing. Okay, let's see if I can get the pictures good enough for you to handle today. So here we go. Now let's imagine, here's my little half slit. Let's pair off two of these like I did to point P. So here's point P, and here's another one. Ooh, not quite straight. I hate it when it does that. Okay, let's go back up here to draw. Silly monkey. This is the triangle that I always have so much trouble drawing straight. I just really struggle to get that one because it's so narrow. There we go. And there's that triangle we were talking about. So what I'm going to do is I'm going to pull out what we've got. So we have one triangle. Let's draw it over here. Here's my width. Here's that right angle. This is the width sine theta. And this is theta. Now, when I get over here to point P, somewhere far, far over to the right, erase this out of the way. If I continue this line up and over, and I continue this line up and over, we get another triangle that has a right angle. So two right angle triangles. And this triangle if I think about this, these two, if I make another right triangle in here, these angles are almost right angles. Both of these are almost right angles. And if I split the angle in half, what I've really done is I've made a really big, long, skinny triangle. See if I can get that to insert for me. See if I can right triangle. So what I've kind of got going on here is, let me try this. Come down here. Got this really long triangle like that. Okay? And I'm going to rotate him around so that you can, okay. So this right triangle, you'll notice that if you look at the edges down here, whoops, if you look at the ends down here, those two angles look awfully close to right angles. They're not right angles. We sort of say they are here and here, but they're not really. We're awfully close to being right angles. But what this does is you can see that that triangle that sort of the stick on to the one I drew. So here's my, this guy is right here. These guys are up here. The two legs are almost isosceles. So the fact that these two are isosceles, even though it should be a right triangle, and you know you can't have two right angles in a triangle because they have to add up to 180 degrees. So if this is 90 and this is 90, this would be 0, which is not possible in a triangle. But what we really have going on here is we're making a few things that are called small angle approximations. And so we're going to make some assumptions here that you need to kind of hear. And I think that was what I was really doing a miserable job of the other day. So if you'll imagine that this angle is like 89 and this one is 89, that would leave us a 2-degree angle over here. Which if I then split in half, these two triangles being similar, now this angle up here is going to be very similar to another triangle, which I shall now draw. Okay, triangles, let's do it. So now consider a triangle that goes from that midline straight across and straight up so that this is Y. Usually call this distance, distance to screen. And then Y is the distance to the fringe. What we have is that this angle right here and the little tiny one, if we, this is going to be so hard, if I divide this one in half, if I just take one of those, if I just take this one as the top half of that little buddy system there, that angle right here and this angle right here are going to be the same because the lines are almost parallel. And so what we get is we get two more similar triangles. Once again, I'm going to try to draw those out so that you can kind of see where we're going with this. So let me erase this part, and then I will see if I can't, on the bigger picture, show you where I'm talking about. So let's do that real quick. And then we're just going to move on, and I'm going to give you the math derivation. So let's put some, first of all, shapes. Oh, pardon me. Boy, I need that line. Could we possibly get a, like, fat line? What the heck? Okay. Here's my fat line. Here's my slit. Now let's try this. So we have one right triangle that does this, except that I'm going to need to rotate him this way. I know, crazy, right? Okay, so there's one triangle. And when I draw on this now, this is Y and this is D. So let's say this is my first dark, just to give you an example. Okay, so there's my first dark. In the meantime, I also have a triangle that is doing this. This one's going to be more fun to try to figure out how to make it do what I want it to do. That's good. Let's make him orange. Okay, let's rotate him. He's laying the joys of what we have to deal with. What I want, well, I don't know if I'm going to get what I want here. I want the tip down here. So I think what you're going to have to live with, yep, it's not going to, it's a little too structured in how it lets me move things around. So I'm not going to spend all night doing this. You can see the two triangles I'm talking about. These two triangles are going to be similar to each other. So here's the hypotenuse, hypotenuse, right angle, y goes with y. So we have all these similarities so that this angle and this angle are the same. So that's where all our math is going to come from. The fact that we can make this angle and this angle's really close together. They're not the same, okay? It's a model, but it's a model that works really, really well. And this angle down here and this angle up here are the same. So we've got a lot of triangles that we can work with. So let's get on to what we actually do with the math here. So to go from the from that second, the orange triangle that we were working with, let's give you what we've got there. We know that when we're working with, we've got dark fringes and we've got light fringes. And we know that light fringes are constructive and dark fringes are destructive. So this is constructive. This one is destructive. And what we get is that extra path difference in both cases is going to be, it's going to act like a half width slit. So we don't use the whole slit. We actually, single slit uses half the width instead of the whole width of the slit. It uses half the width because what we have to do is we have to have a photon on top pairing with a photon on bottom, something that's interfering with itself. So we have to treat it, even though there are not two separate slits, we treat it like the big slit is two separate slits that are side by side. So we use half the width, and to do dark fringes, we would get 1/2 wavelength, okay? Or 3/2, 5/2, 7/2, and so forth. Now keep in mind that you have to use symmetry. So if we have one on top, we also have a matching one on the bottom. But here's what happens on the algebra if you watch this. The 1/2s are going to go. So we get 1/2 sine theta, W sine theta equals, and if you look at these numbers, 1, 3, 5, 7, you're going to get a multiplier that counts the fringe, okay? So we're going to have a multiplier of some sort. This is just a multiplier, okay? Don't get strung out by that. It's just a multiplier. Now, here's where we get into the icky bit that is called the small angle approximation. And you may say, Miss Wilson, we've done a lot of approximation on this. Yes, we are. We're assuming that a lot of triangles are similar, and they are. They're very, if you do the geometry and you check values, you'll find that these are very, very similar. So we're going to use the small angle approximation when our angle is less than, I don't know what that's doing, when our angle is less than about 10 degrees, or when our angle is less than 1 radian. And here's what we get on that. Sine theta is equal to the angle itself. So for example, if you put in your calculator in degree mode, sine 2.13 degrees. When you do that, you're going to get an angle. Let me pull up my calculator real quick. Let's see, mode. Need to be in radians. We usually do this with radians, so let's do this with radians. Let's not worry about this one. It's a little bit harder to prove that one. But let's say we do the sine of, since it's 1 radian, let's do 0.75. So if I do the sine of 0.75, that answer is mode is 0.68. You say, Miss Wilson, that's not terribly close. And I'd say, yes, you're correct. This number is very close to 1 degree. But if I go to 0.5, I get 0.4794. If I do sine of 0.25, I get 0.2474. If I go to sine of 0.10, I get 0.0998. And I think you can see that when we're looking at these, as you get closer to 1, they get worse. As you get closer to 0, they get much, much better. And remember, these are very tiny angles. We're talking about a slit width that is near the wavelength of light. So it's in nanometers. And then the angle that it makes is just literally in decimal places of angle. So we're almost always below, definitely below 0.5 radians, and most of the time much closer to 0 radians, 0 point something radians. So the small angle approximation says that sine theta equals theta. And let me give you, for those of you that don't feel real comfortable with that, let me give you an example of why that happens. So here's a circle. We've got our coordinate plane in there. If I draw a very small angle right here, here's x, here's y, and let's make our radius 1. We call it the unit circle. X over 1 is the cosine of theta, and y over 1 is the sine of theta. Okay? You may notice that this would be a triangle whose hypotenuse is 1, but whose x value is 0.9998. This would be 0.0002. Is that the right number of zeros? Yep. So y value is tiny, 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 tiny. But then again, the angle is tiny, 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 tiny. So those two values are the same. So wherever we see sine theta, we're going to write theta. We're going to go one further on that, and here's where we're going to go. Tangent of theta is also equal to theta is equal to sine theta. Now notice this is about equal to, not identical. Because what happens on this tiny triangle? Well, let's see. Tangent is sine over cosine. And we've just argued that the cosine is really, really close to 1, which means tangent is equal to sine. But sine is equal to theta, so tangent is equal to sine is equal to theta. Now, for those of you that don't feel comfortable about this, I'm really sorry, but this is one of those times when calculus actually proves that this approximation is correct, but you have to have had, a couple of semesters of calc before you see that. So just bear with me. So here's what's going to happen now. Going back to our dark fringes, we have W sine theta. Stop doing stupid things. W sine theta equals some sort of multiplier times here, okay? And I'm going to show you where the multiplier comes in, so you're going to see this real quick. Let's leave that off for just a second. So we have 1 here, 3/2 here, but the half got canceled. Then we have 5/2 would be our next one. So what happens is we go W times theta equals 1 wavelength, or W times theta. Notice these would be different wavelengths. Okay, this is 1. First bright fringe, second dark fringe, third dark fringe. Sine theta 2 equals 3 wavelengths. Of course, W theta 3 would equal 5 wavelengths. And so what we get here is that your angle of your angle, that's not going to let me erase that. Your angle, holy heck, stop doing that. My angle oy vey. Let's get down here where I can't bother that. The angle for your first one will be 1 wavelength over your slit width. Your angle for your second one will be 3 wavelengths over your slit width. Your angle for your third dark fringe would be 5 wavelengths over your fringe. So that's the first piece. So what we have is our angle measure is equal to some number times the wavelength over the slit width. Okay? So that's how you get your dark fringes. That's the equation you use for your dark fringes. Okay? That's the first part. Now, the second part is, what if we want to do bright fringes? Well, bright fringe is going to work the same way. Half the slit width times sine theta equals 1 wavelength, or half the sine theta equals 2 wavelengths. So what we get here is W sine theta equals 2 lambda. W sine theta equals 4 lambda. So W theta 1 equals 2 lambda. So theta 1 equals 2 lambda over W. Theta 2 would be 4 lambda over W, and so forth and so on. So you'll notice for light fringes we get 2, 4, 6, 8. For dark fringes we get 1, 3, 5, 7. So we get odds for darks, evens for lights. Okay? All right. Now, last part. Last part. How wide is the central maximum? So let's, one more picture. How wide is the central maximum? Well, let's trip this across over here. And let's say this is my first dark fringe. And of course there's another dark fringe. First dark minimum, first minimum of light. There's one on each side, but I'm really only going to worry about this one. We know the angle. This is Y, which is how much you go up or down, and this is a capital D, which in your book they're going to use L for length to screen. Length from slit, if you will. And so if you do tangent of theta equals Y over L. Now remember, from what we just did up here, I'm going to scroll back up now, that tangent of theta equals sine of theta equals theta. What was sine of theta? Let's go back and look at any of these. Sine of theta, if we're doing dark fringes, let's come back over here. That first dark slit equals 1/2 wavelength. The halves cancel out, and I get W sine theta for the first dark fringe is wavelength. So sine of theta equals wavelength over W. And then theta and sine of theta are the same thing, so theta equals lambda over W. But my width of my central maximum is 2 times that big. So whatever y is, it's 2y. So tangent of theta, which is lambda over W, tangent equals sine equals theta, is 2y over L. So we get L times wavelength over 2 times y equals your width. So I cross multiply. I get lambda times L equals 2y width. Width here is this. Keep in mind, this is width of central bright. Wow, so that was a lot of stinking geometry. So let's do a couple of problems really quick. Okay, let's do a couple of problems really quick. So I'm going to make a new page. Let's do number 62 and number 63. And these are on page 563, I think. Let me look. Yeah, 563. Okay, both on page 563. So we did an hour's worth of lecture to teach you where all the geometry comes in. Now what we've got to do is just work the problems. I told you the math was easy because the setup is hard. So let's look at 62. We have wavelength of light is 589 nanometers. We know that, let's see, the distance from the slit to the screen, so that's L or D, it doesn't matter to me which one you call it. D or L is 75 centimeters, so that would be 75 centimeters. And we know that Y3 minus Y1 is 7.5 millimeters. So in this case, if here's my first dark, so here's dark, this is first dark. Third dark, remember, because these only count odds. You only count odds for dark, you only count evens for light. So the distance from here to here is the 7.5 millimeters, which is actually kind of aggravating because what they're going to ask me is, what is the width of the slit? So let's get back to our ideas that we had a minute ago. Slit width is going to be equal to, and we come back down, I'm going to show you. Oh, wait, I did a whole new page, didn't I? So it should go the other way. Well, never mind. Is you get you have 2 times your wavelength, and you want to do this 2 times your wavelength times L, so 2 wavelengths times L, and all that over your slit width. So width of central bright is equal to this setup. Okay? Now, I can show you, let me back the train up because I know where the other one is. You'll notice that this is also L times lambda over 2y if you know y. We don't happen to know y. See, the problem is we know these two. We don't know that one. Okay? So I'm put that back down and get the other one back up. So here's what we've got to do. Well, let's see. What is y3 minus y1? y3 minus y1. Well, let's see. y3, if I do that again, be w over 2 sine theta equals 3/2 lambda. And y1 be w over 2 sine theta equals 1/2 wavelength. Just trying to figure out what I know and what I can use. And so then the halves cancel out. Halves cancel out. And so I know that, let's see, this would be 3 lambda over W would equal theta 1, and 1 lambda over W would equal theta, whoops, this is theta 3, and this is theta 1. Think to myself, what can I do with that? Well, that doesn't feel like it's terribly helpful because I don't know either angle, right? I don't know what the angle thing is. So let's back the train up a little bit. These angles, I don't know. But it's okay because I don't really need to know those. What I really need to know is the fact that they're this far apart. So I know that y3 minus y1, remember that these are equal to the y values. Remember, we do that long scrawny triangle that y is equal to theta. The side length is equal to theta. So let's do this. y3 minus y1 equals 7.5 times 10 to the negative third. Well, that equals 3 lambda over W minus 1 lambda over W equals 7.5 times 10 to the negative third. 2 lambda over W equals 7.5 times 10 to the negative third. Hey, 2 times 589 times 10 to the negative ninth over W equals 7.5 times 10 to the negative third. So, cross multiply. I have no idea what that number is. Calculator. 2 times 589 exponent 9 that's negative equals 0, 0, what was it, 1, 1, 1, 1, 7, 8. Oh, 1, 2, 3, 4, 5 zeros. Okay, now I can go back. 1, 2, 3, 4, 5, 1, 1, 7, 8. And this is W. So then I divide both sides by this. And I get the slit width is, come back over here, calculator, divide that number by 7.5 E, 3 negative, equals 1.57 times 10 to the negative fourth. Somehow that doesn't sound right to me. What have I missed? I feel like I've lost L. L should be in here someplace. Oh, shoot, it is. Hang on just a second. Miscopied my, I didn't, looky here. I got to copy my formula right. Let's go back over here. We got L times lambda. L times lambda. On this one, we've got, this is L times lambda to get this triangle. Okay, sorry. I'm skipping too far back for you. Let me get this minimized and come back over here. Let me clean this up. Everything was right. I just miscopied the formula. All this argument is correct. Let me just go back. Let me come back to the beginning and show you where I'm going. And let's write the right formula, because that would be helpful. Yes? Yes. Very helpful. Okay. So, this is the width of the central bright. The Y value, when you go up and down the screen, is going to be the multiplier lambda wavelength over slit width, because if you recall, we had this is to your first, so if we're doing our screen, here's our first dark, And that's, so our first dark would be this. Our third dark would be this. But the distance here is y over d equals the multiplier times L. So you have to get how far away from the screen you are. So your tangent equals your sine, and your sine is going to equal, hang on just a second, to be consistent with what the book does. They call this L. So y over L would be tangent of theta, this angle right here. So y over L equals, we're going to change out the tangent here. And remember, this is, so the tangent, we're going to change that out for p lambda, because the angle depends on which fringe. So you need the counter here. And then over that, you would have slit width. So this is our other equation for up and down the screen. Okay, so then we cross multiply, and we get this. So the y values are p lambda L over W. And like I said, I know that's a lot of geometry. We will practice with these formulas some more, so you'll get really good at them. So what we have here is we have 3 wavelengths times length over W minus 1 wavelength times length over W, because it gets bigger on the screen the further you go out from it. And then that equals the 7.5 times 10 to the negative third. So we get 2 lambda L over W equals 7.5 times 10 to the negative third. So 2 times 589 times 10 to the negative ninth for nanometers. 75 centimeters would be 0.75 meters. And all this is over 7.5 times 10 to the negative third. And if I do the number crunching there, that is going to give me, I'll swap these two's place, and that'll give me my width. So I cross multiplied here to here, here to here, and then I divide by the 7.5. So the width comes out to be, what did I get on that? 2 times 589 e negative 9 times 0.75 divided by 7.5 e negative 3. And that gives me 1.2 times 10 to the negative fourth. So 0.12 millimeters, or 1.2 times 10 to the negative fourth meters. So 62 is a little tricky because you have to rewrite that statement using which fringe you're working with. But you can see that the algebra comes out pretty straightforward. It's really just fill in everything. Okay, so that's 62, so let's do 63. 63 is actually an easier problem. So 63, we've got a bat coming out of a cave, and it's making echolocation sounds. So we know that our distance away, distance to our location, our screen, is going to be 100 meters. We know that it's a 30 centimeter wide crack, so this is 30 centimeters. And we know that the speed of sound is 340 meters per second, and the frequency is 30 kilohertz, sorry, not 100, 30 kilohertz, and that's our frequency. So this problem requires us to do something. We need to find wavelength. So this is a two-step problem as well, just like the last one. To find the wavelength, I know that speed is wavelength times frequency. So that's where this number is going to come into play. So 340 equals wavelength times 30 times 10 to the third, because it's 1,000 kilohertz. So this number comes out as, sorry, I got the hiccups, is going to be 340 divided by 30123, and we get 0. Sorry, man, I really got the hiccups. 1133. Okay. So now we're ready to work our problem. Our problem, we go back up here and we look at, we want to find the width of the central bright, is what they're asking me to find. So here I go. Central bright, copying the formula from above, 2 lambda L, 2 times the wavelength times L, over slit width. So this equals 2 times 0.01133 repeating. Distance is 100 meters, and the slit width is 0.30 meters, because this is in meters and this is in meters. And so we get the width of the central bright. Central bright width is 2 times 0.011333333 times 100 divided by 0.30 is 7.6. 7.6 meters. So if you stand behind the crack, so here's the crack in the wall, and if you're out here at 100 meters, if you stand in a region that is 7.6 meters wide, you're going to be right in the middle of the happy little bat noises. Okay, so we're going to give you some practice problems and work in class, and we'll pick up on this next time. Thanks for your patience, and I know it's a long video, but hang tight.